In this lesson, we're going to talk about the format of IPv4 addresses. So first of all, an IPv4 address has 32 bits or 4 bytes. That's 2 to the power of 32 different combinations. And that's approximately 4.3 billion unique addresses. Let's look at an example. Here's an IP address written in binary format. Here we can see that we actually do have 32 bits in an IP address. The first section has 8 bits. The second one has 8 bits. The third one has 8 bits. And the fourth one also has 8 bits. We have 4 sections of 8 bits. Those sections are called octets because we have 8 bits in it. It's an octet. But this is just a binary representation. An IP address, an IPv4 address, is typically shown as 4 decimal numbers, which we can see here. So this is the example from the previous slide, and these are the decimal values of the same example. And these are the octets. We count the octets from left to right. The first octet is 98, the second one is 188, the third one is 19, and the fourth one is 71. But we don't really write an IP address like this. We add dots. We add dots between the octets, but we do not add a dot at the end of the fourth octet. Here's what this IP address looks like. It's 98.188.19.71. Now that we've talked about the singular octets, let's talk about portions in IP addresses. The first part of an IP address is always the network portion, and the second part is always the host portion. We can actually have one more portion in between. It's called the subnet portion, but we'll discuss that later. For now, just remember that you can't mix the two. So you can't use the first octet, for example, the first octet as the network portion, and then the second octet as the host portion, and then the third octet as network portion again. So you have to, once you're done with the network portion, the host portion begins and there's no more network portion in it. Now in this example, we have 2 octets that belong in the network portion and 2 octets that belong in the host portion. But it doesn't have to be like that. We can have 10 bits in the network portion and then the other 22 bits in the host portion. But we wouldn't be able to draw this like this. We would have to split the two. So for this example, or for what I've talked about up until now, this is only for /8, /16, and /24 networks. And I'll talk about this format. It's called CIDR. We'll talk about this later, but for now, know that you can actually split one octet. You don't have to use an entire octet for a portion. Okay, now let's talk about the reason to split an IP address into 2 parts. Here we have a small network, 1 router and 3 switches. For the purposes of this example, this server farm or a small data center really is just a small network where we have 6 devices that require each 1 IP address at minimum. Each of these 3 networks is connected to an interface on this router. This interface is going to be the default gateway for all of the devices that are inside this network. This interface is going to be the gateway for these devices, and this interface is going to be the gateway for all of the servers that are in this network. Each of these interfaces is going to have an IP address. Let's look at those addresses. The gateway for the server network is going to be 10.0.1.1. The gateway for the second network is going to be 10.0.2.1, And the gateway for the third network is going to be 10.0.3.1. These are the network portions of each of these addresses. You can see that these are actually different networks. The point of the network portion is to differentiate different networks. Let's look at what IP addresses are going to be assigned to our end devices. The servers are going to have addresses like 10.0.1, 10, 10.0.1, 11, 10.0.1, 13. I hope you can already see the part that's being repeated. So all of these devices are going to have addresses that begin with 10.0.1. That's the network portion. The network portion of an IP address is going to be repeated through the entire network. For this LAN, it's 10.0.1, and the host part changes for each device. The first IP address was assigned to the gateway, and then we reserved, that's the term used in DHCP, we reserved or we excluded the first 9 addresses from 1 to 9. And then we begin assigning addresses to end devices from 10 upwards. Now let's look at our second network. All of the devices have IP addresses like 10.0.2. something. The first laptop is 10.0.2.10, then the second one is 10.0.2.11. You can again notice the rule here. The network part is the same for all devices and for the gateway. In our third network, we got the same situation. The gateway is 10.0.3.1 and the end devices have addresses that begin with 10.0.3. Now that we've covered the types of addresses we would assign to gateways and end devices, we need to talk about 2 other IP addresses that are very important. The network address and the broadcast address. The network address is the very first IP address in a subnet. In the previous slide, we gave the first useful IP address, or the first usable, I believe is the term, IP address to our gateway, but that's not really the first IP address. The very first IP address in this subnet would be 10.0.3.0. Here we have an example, 81.2.0.0, where the first 2 octets are the network portion and the second 2 octets are the host portion. The network address has its host portion filled with zeros, and the broadcast address is the opposite. A broadcast address is the very last IP address in a subnet. Here's an example, 81.2.255.255. So 81.2 is the network portion and 255.255 is our host portion. Hopefully you can notice our host portion this time is filled with ones, and this is what it looks like in binary format. We have 8 ones in the third octet and 8 ones in our fourth octet. Now let's look at some examples. The right part of this network is actually the same network from our previous example, but now we've added one router which gives us 2 additional networks. We have this network between the 2 routers and this small LAN with 2 laptops. We're going to describe these 2 networks with their network addresses or their network IDs. This point-to-point network, a point-to-point network is a simple network between 2 routers. it's going to be 9000. So this is our network ID. The small LAN with 2 laptops is going to be 8000, and here are the end host IP addresses in these 2 networks. So we assigned the router on the left with 9001 and the router on the right with 9002. These are the 2 IP addresses we're going to use in this network, and in this network, we're only going to need 3 IP addresses, one for the gateway and one for each of the laptops. They're going to be 8001 and 80010 and then 80011. Now let's think about what are the network IDs for the 3 networks we had in the previous example. I'm just going to make this easy and display the network IDs. For the first network, it's going to be 10030, as we've talked about in the previous slides. So the network ID is the network portion of an IP address, and then the host portion filled with zeros. The other 2 networks are obviously going to be 10010 and 10020. The next thing we're going to talk about is what are these network IDs or network IP addresses actually used for. And the example I'm going to give you is going to be related to routing. So we're going to look at how do we build routing tables and what do they actually look like. So we're going to circle this 10.0. something network, and we're going to name our routers R1 and R2. We're also going to have to name the interfaces on our routers. So they're going to be interface 1 and interface 2 on router 1, interface 3, 4, 5, and 6 on router 2. And then we're going to look at what the routing table in router 1 looks like. A routing table lists the different networks that this router can reach. So router 1 can get to all these networks by simply sending packets to different interfaces. So a job of a router is actually to just get rid of a packet as soon as possible. Now, for example, if router 1 didn't have an entry for the network 10.0.3.0 in its routing table, it wouldn't be able to reach that network. So if it received a packet with a destination IP address that belongs to that network, it would just drop the packet because it doesn't really know where to send that packet. Fortunately, we do have an entry for that network, so router 1 is perfectly capable to send packets to that network. But now let's do something a bit advanced, and we'll cover this topic further in our future lessons, but I just want to show you what's possible with IP addressing and or IP subnetting in this example. We're going to look at this 10.0.123 network, and I promise to explain what this means further in probably the next lesson. But for now, just know that /16 means that the first 16 bits represent the network portion of this IP address of 10.0.0.0. So what I want to do here is I want to replace these 3 entries in our routing table with only this. Why can I do that? So when router 1 receives a packet with a destination address of 10.0.2.50, for example. Okay, even if it doesn't exist here, let's say we add a new device here, and we give it that address 10.0.2.50. So say that this laptop wants to send a packet to that imaginary device. Okay, so this router will look up the destination IP address, which is 10.0.2.50 in its routing table, and it's going to say, okay, so I have a route for 10.0.2. something, so anything. So this is a network address. It represents all hosts within 10.0.2 network. But before router 1 can reach this route, it has to go through all the other routes. So what I want to do is I want to simplify the process here. I'm just going to replace these 3 routes with one route. So this is basically called a summary IP address, but we'll talk about that later, I promise. But for now, what happens here is this router receives a packet with destination address 10.0. something. So the last 2 octets could be anything. So it doesn't have to go through 3 routes. Instead, it only goes through 1 route because anyway, it's going to send a packet with a destination address of 10.0. anything through interface 2. I hope that made sense. We'll talk about this further, but just to give you an idea of what's possible to do with IP addressing. And now we're going to talk about broadcast addresses, what they are, and to give an example of how they work. We've already defined our network IDs for all of our networks in our example, and I'm going to use the CIDR notation once again, and I promise that the next lesson is going to be about that, and we're going to do more examples. But for now, just know that /24 means that the first 24 bits, or 3 times 8, which is 24, or the first 3 octets represent the network portion. So 8.0.0 is our network portion, which is exactly 24 bits. So how do we figure out what's the broadcast address there? Well, we simply take the host portion and we turn it into ones in binary format. In decimal format, when we have 8 consecutive ones, that's 255. So the broadcast address here is going to be 8.0.0.255. So 8.0.0 is our network portion, and this last octet is our host portion. If it's filled with ones, it's going to be the broadcast address, and if it's filled with zeros, it's going to be the network ID or the network IP address. Now let's look at the other networks. So for 9.0.0.0/24, that's going to be, the broadcast IP address is going to be 9.0.0.255. Hopefully you can already guess what the broadcast addresses for the other 3 networks are. So we're going to use the /24 for all 3 of them, and all 3 of them are going to be the same network portion, and only the host portion is going to change from 0 to 255. Let's look at an example. Let's say that this laptop sends a broadcast packet with source address, its own address 10.0.3.12, and destination IP address is going to be our broadcast address for this subnet, which is 10.0.3.255. So once this laptop sends its broadcast packet, it's going to end up on the switch. The switch is going to send this packet through all of its interfaces except for the interface that received the broadcast packet. So these are the devices that end up receiving the broadcast packet. Now, if you're wondering what is the router going to do, is the router going to further forward this broadcast? It's not. So routers do not forward broadcast packets. Hopefully that's clear enough. We're just going to look at one more example of how to determine a network ID address and how to determine a broadcast address. So in this example, we're going to use host address 153.0.99.207. And this is the binary representation of this address. The red part is going to be our network portion, and the blue part is going to be our host portion. So to determine our network address, we're going to just copy the network portion, and into the host portion, we're going to put all zeros. So this is our network address. It's actually going to be 153.0.0.0. How do we determine the broadcast address? We're going to copy the network portion, and we're going to use ones instead of zeros in our host portion. There you go, guys. That's it for this lesson. We'll talk about network masks and the CIDR format and all of this further in our future lessons. See you there.